Hello and welcome to my video on orthogonal diagonalization. In this video we're going to be presuming knowledge of eigenvalues, eigenvectors, and the characteristic equation, as well as a basic understanding of what it means for two vectors to be orthogonal and what it means to normalize vectors. So let's get started. So the orthogonal diagonalization builds on matrix symmetry. So this only works on a symmetric matrix. So we've got our symmetric matrix A. What we're doing very simply in an orthogonal diagonalization is we are breaking it down into this decomposition. Now, obviously this is a diagonalization because if the matrix is symmetric, this is equivalent to P inverse. Now, what are we doing in this specific diagonalization? So P here is going to be comprised of the normalized eigenvectors of A. So let's just assume A is 2 by 2. That would be V1 and V2. And D is going to be our eigenvalues, lambda 1 and lambda 2. And then of course P transpose is just going to be the transpose of P, but you know, I mean, you could also write this as V transpose V2 transpose. So what are we doing here? So obviously this matrix has to be square because it has to be symmetric. Obviously it has to be symmetric because it has to be symmetric. If it doesn't have distinct eigenvalues, this gets a bit more complicated, and I'm going to cover that in the next video. So for this one, we're just going to work with a matrix that has distinct eigenvalues, and it should have orthogonal eigenvectors. If it doesn't, if it has, you know, two eigenvalues that are the same and then non-orthogonal eigenvectors, that gets a bit complicated. You have to use Gram-Schmidt, but let's ignore that for now, and let's just understand what we're doing here. So let's take the matrix 0, 1, 1, 0. Which is symmetric. Well, let me go ahead and prove it. A, and then we just do the transpose. It is most definitely symmetric. Now to find its eigenvalues, we just do A minus lambda I, and we find minus lambda, and 1, 1 over there. And so if we assume the determinant of that is 0, we get lambda squared minus 1 equals 0. And since we know lambda squared equals 1, we know that our eigenvalues are 1 and minus 1. So that gives us D, which is just 1 minus 1 there. And then we'll need our eigenvectors. And obviously to do that, we just take A minus lambda I. So in one of these cases, it will be minus 1, 1, 1, minus 1. And if we just look at the null space of that and try and derive a vector, end up with 1, 1. To normalize that, we just go 1 over root 2, 1 over root 2. So that is our V1. So that's the first column. And then let's try A minus lambda I for our second eigenvalue, and we end up with 1, 1, 1, 1, 1. And if you just look at the null space of that, you'll end up with either 1 minus 1 or the other way around, depending on which you choose to identify as the pivot. And if we normalize that, we end up with over root 2 again. And so we can finish off our matrix over here. And obviously we'll want to take the transpose of that, but that's very straightforward to do. In fact, I think that P itself has ended up symmetric in this case. And so we arrive at the orthogonal diagonalization. And this is, I mean, with most decompositions, the purpose, it has some advantages, but its widespread use in the modern day is computational, because it can save computing power, and because because symmetric matrices are a big part of a lot of computations and algorithms for instance, the normal equations, this decomposition becomes quite useful. So we've covered how to do a orthogonal diagonalization for a matrix with distinct eigenvalues, orthogonal eigenvectors. In the next video, we're going to cover how to go about an orthogonal diagonalization for a matrix that may not have distinct eigenvalues and therefore may have non-orthogonal eigenvectors. Thank you.